Welcome to the deep dive. For centuries, we've been wrestling with, a really cosmic question. Does the universe have enough stuff in it to eventually stop expanding and collapse back in on itself in a big crunch?
Or does it just expand forever?
Exactly. And today, we're diving into the grueling, decade-long technical journey led by Saul Perlmutter to answer that, and how they ended up with an answer that nobody saw coming.
Well, it started with Edwin Hubble, right? He confirmed the universe is expanding. The next logical step, which scientists chased since the 1930s, was to measure its deceleration.
How much gravity was, putting the brakes on everything.
Precisely. And for that, they needed a very special tool, the Type Ia supernova. The idea was that these exploding stars could act as standard candles to measure immense distances, and therefore time.
A standard candle, so if you know its true brightness, you can figure out its distance just by seeing how faint it looks. And that distance tells you how old the universe was when the star exploded.
That was the dream. But for about 50 years, it was largely useless.
Why was that?
Because supernovae were notoriously inconsistent. Their peak brightness could vary wildly by a factor of 2, maybe even 3.
So not very standard at all.
Not at all. It wasn't until the mid-1980s that the field really became viable. Two things happened. First, astronomers isolated that Type Ia subclass as being, the most reliable of the bunch.
And the second thing was technology, I assume.
It was the digital revolution. CCD detectors and fast computers finally made it possible to analyze these huge, faint images and, crucially, to process them fast enough to actually find the explosions.
So the tech was finally catching up. But the target itself. Perlmutter described it as a total nightmare. If you had to pick a research tool, you would never pick a supernova.
Okay, absolutely not. He called it the triple threat.
Okay, break that down for us.
Okay, so first, they're incredibly rare. You might only see one explosion in a typical galaxy every, 500 years?
Wow.
Second, they're random. You can't just call up an observatory and say, hey, can I have the Keck telescope next Tuesday for something that is completely unpredictable?
And that telescope time is booked out months, years in advance.
Exactly. And then the third threat, they're rapid. They brighten and then fade away in just a matter of weeks. You have to catch them on the rise to get an accurate measurement of their peak brightness.
So, rare, random, and rapid. That just seems impossible. How do you possibly build a systematic, predictable scientific campaign around something like that?
Well, this is where the real genius of the project comes in, the famous batch strategy.
Instead of hunting for one, you hunt for many.
You hunt for dozens. And to do that, they first had to develop new wide-field cameras that could look at thousands of galaxies all at once. But the real breakthrough was tying their whole schedule to the lunar cycle.
Right, I read about this. How on earth did the moon help them schedule time on the world's biggest telescopes?
It's so clever. They realized if they took their first set of wide-field images just after a new moon, when the sky is completely dark,
Right.
and then waited exactly 2.5 weeks, and took a second set of the exact same patches of sky right before the next new moon.
You could compare the before and after pictures. Any new little dot of light is a supernova.
And not just one. You've guaranteed you'll find a whole batch of them, maybe half a dozen, sometimes more. And because of that 2.5-week window, you've also guaranteed that you caught them before they reached their peak.
Ah, so you could finally make a phone call and say with confidence, in 2 weeks, we're going to have 6 high-priority targets ready for you. You're not guessing anymore?
You're not guessing, you're delivering. It turned a random hunt into a predictable, almost industrial process.
Okay, so they could find them reliably. But they still had to solve that original problem, making them better standard candles.
Yes, the dispersion was still around 40 or 50%. Too high. That's where a technique called the light curve stretch factor came into play.
What's that?
They found a correlation. The faster a supernova faded, the fainter its true intrinsic brightness was.
So a fast one was a 40-watt bulb, and the slow one, a stretched one, was like a 60-watt bulb.
A perfect analogy. By correcting for that stretch, they standardized the brightness and dropped the measurement variation down to about 12%. Suddenly, these were truly excellent distance markers.
And they solved another huge problem, the cross-filter K correction.
Yes, that was a monster. I mean, it's key to comparing old versus new.
How so?
A distant, high-redshift supernova is flying away from us so fast that its light is literally stretched into the red part of the spectrum. So you're seeing it through a red filter.
Okay.
But a nearby one is mostly seen through a blue filter, and you can't just directly compare a red measurement to a blue one. It's apples and oranges.
So the K correction is the formula that turns the apple into an orange so you can compare them.
Precisely. It lets you know you're measuring the same physical event, whether it happened 7 billion years ago or 100 million years ago.
So by 1994, it seems like they cracked it. They've overcome all these logistical, technical, mind-bending obstacles. But then the first bits of data start coming in, and there's a problem.
A big one. There just wasn't as much gravitational slowing as everyone expected. The universe seemed to be coasting, almost.
Which brought back an old idea, something Einstein himself came up with and then threw away.
The cosmological constant, a sort of anti-gravity force, a repulsive energy woven into the fabric of space-time itself that was pushing things apart.
And to figure out if this mysterious force was real, they had to look even deeper into space.
Much deeper, to a very high redshift supernovae, because that far back in time, the universe was denser and the pull of gravity for matter should have been much stronger than this new force. They were still expecting to see deceleration, even if it was just a little.
But when the final results came in, from all 42 supernovae, the universe wasn't slowing down at all.
Nope, it was accelerating.
It's just hard to wrap your head around that.
It's completely counterintuitive. And the data told an amazing story. For the first 7 billion years of cosmic history, gravity was winning. The expansion was slowing down, just as predicted.
But then something changed.
About 7 billion years ago, it seems this strange, repulsive force, what we now call dark energy, became the dominant force in the cosmos, and the expansion started speeding up.
So the ultimate takeaway here is that the biggest answers in science, they don't just come from a single flash of brilliance. They come from a decade of just relentless, grinding problem solving.
Absolutely. The discovery of acceleration was what Perlmutter called better than great, because it didn't just close a chapter, it blew the doors open on a massive new mystery.
It essentially confirmed that 70% of our universe is made of something we know almost nothing about.
A monumental puzzle left for the next tag teams of scientists, as he put it.
And it really makes you think, what other fundamental forces or truths are just sitting there, completely invisible to us, just waiting for someone to finally invent the right kind of wrench to tinker with the universe and find them?